Contactless palm print and knuckle biometrics for mobile devices by Team Picard. For our case study, we analyzed the 2012 study published by Mikhail Koraz and Rafal Kozik in the Pattern Analysis and Applications Journal. The overall purpose of the study was to propose the use of palm prints and knuckle prints for biometrics and to identify a way to extract those prints for easy identification. Many of you are probably familiar with biometrics in terms of eye scans, fingerprints, or facial recognitions. But biometrics is evolving. It's no longer a sci-fi fantasy of the future. However, the use of biometrics is still early, and current issues with its implementations can sometimes be a barrier to use. Biometrics today suffer from scalability problems, overall effectiveness, security holes, general user-friendliness, and high infrastructure costs. The researchers in the study are proposing contactless human identification. What does contactless mean? It's a way to identify individuals with unsupervised images, meaning a person does not have to analyze the images. Rather, a computer program can do so. In addition, it's the use of a person's own device, namely the mobile phone. It circumvents the need to touch a public hardware system to collect the biometric data. So why is it better? It uses existing infrastructure, thus greatly reducing the cost to implement biometric collection. And because it uses mobile devices, there's already a high penetration of the required hardware already achieved. The researchers used a series of pictures both from participants willing to provide them and from an existing database of images. They then use a specific algorithm to define the identifiable areas on both the knuckles and palm prints. We will provide more specific details on their approach in the following slides. The first analysis in the study was done on palm prints. The paper did not present this high-level plan directly, but it's good to talk about what they were trying to accomplish at a high level before diving into the nitty-gritty details of how. How do you compare palm prints? The same way you compare fingerprints. You have to look at the crevices and see if they're the same. This can be challenging for a computer because all palms are different. They vary in size, they have different lengths and different widths. Some people have smaller fingers, wider fingers. Others have completely different curvatures. And finally, people have different skin colors. They follow these steps to begin identifying the palm print. Step 1. Remove skin color. 2. Distinguish the palm from the background. Step 3. Identify the significant points. And step 4. Eliminate the rotation of the palm in the image. After this, they should have an image of the palm with a common rotation. Then, to remove size and shape differences, they follow these steps. Step 1. Crop the image to only contain the palm. And 2. Translate the identified points of significance into a vector. Finally, they need to identify where the crevices are in the image. They do this by applying a projector of the final vector into a common space or mask. They use 3-valued masks for performance reasons. How they determined these masks was the point of this experiment. There were 3 methods used to generate masks. In the random method, they generated a matrix, then they set all positions in it to 0, and they randomly chose a position and randomly set it to -1, 0, 1. In the manual method, several people were tasked with manually identifying in a palm vector every bright, dark, and normal area. At least 50 masks were generated by each person. And lastly, the Eigen-Palms method was a computer-run process of automatically and intelligently generating the masks. They do this by applying PCA, or Principal Component Analysis, which is a statistical technique used in facial recognition and other image recognition processes to find patterns in high-dimensional data. They would read all the palm prints from a database and automatically determine where the most likely location of a crevice was. It would then generate masks corresponding to these probabilities. Knuckles as biometrics. There are a number of advantages in using knuckle images as a biometric source. They have a distinctive set of features that can be captured well by digital cameras, and they are easily accessible. However, the use of knuckle images also involves some challenges. To use them as a biometric source, a security system has to translate and store a user's knuckle features into a clear and unique digital record for biometric comparison. It has to do the same translation process for knuckle images presented for system access. Additionally, the system has to accommodate interaction with users by handling differences in skin tone, knuckle rotation, and position. The authors of this study addressed these challenges through a multi-step procedure. They translated the photo images of knuckles into a black and white digital map and then refined it. They used this map to identify key points where there was the highest contrast between a knuckle line and surrounding skin. These points were then used as a basis for comparison between a knuckle image on file for a user and images captured during an access attempt. Since every person's knuckles are different, both in terms of lines and skin tone, the researchers chose to digitally map a user's knuckles by identifying differences in brightness within each knuckle image. They first did this by examining each pixel of the knuckle image as the center of a 7x7 grid and recording pixels as part of a line if they were significantly darker than surrounding pixels. This digital map of knuckle lines was then refined to fill in blank spots that might have been missed. The researchers used a technique called PHT, or probabilistic hue transform, which involved sampling the pixels in random order and again testing their brightness relative to nearby pixels. As you can see from these images, this helped to catch line pixels that might have been missed and created more robust lines in the digital map. The final step in this process was to apply a technique called SURF, or Speeded Up Robust Features, which involves calculating and ranking the significance of differences in pixel brightness within a knuckle image. The pixels which had the greatest contrast with their neighbors, generally pixels at the edge of knuckle lines, were selected as key points and marked on the digitized knuckle image. You can see them here marked in yellow. When a user attempts to gain access using this biometric system, multiple knuckle images are captured and digitally mapped, and this becomes a query for the biometric system to test. The images then undergo the same process as the template image. In the end, the key points in the 5 closest query images are tested against the user's template, and the system reports the degree of agreement between the template and the best query image. The experiments and results of the proposed palm print and knuckle feature extraction methods. During experiments, the system threshold value was estimated to provide the lowest false acceptance ratio, or FAR, that would be equal to false rejection ratio, or FRR. The palm print study utilized the researchers' own database of 252 images. The photos are of 84 different people and 3 images of their right hands. The photos were taken with standard mobile devices. The resolution of the images is 640 by 480. 10% of individuals in the database were used as imposters, while the remaining 90% of images were used as genuine samples. The findings of the mask-based palm print biometrics for mobile devices showed that more than 50 masks does not increase system effectiveness, while increasing the resolution does improve results of the system. The mask extraction method proved to play an important role in the study. The EigenPalms PCA was the best mask extraction method, while humans performed the worst. The palm print portion of the study concludes that the best extraction approach is EigenPalms principal component analysis. The knuckle biometrics portion of the study used an image database called the ITT Delhi Knuckle Database for testing. Over a period of 11 months, 790 knuckle images were obtained from 158 different people. The classification strategy uses SURF descriptor to choose the closest match, after narrowing down 50 choices from basic vector by selecting 5 images on the basis of PHT feature vector. The combination of PHC and SURF proved to be the most effective. PHC alone performed better than SURF alone, with a classification error of 95.56% versus 85.75%. It was found that PHC and SURF complement each other's weaknesses. PHC was better at finding matches between the query knuckle and the template, but SURF was better at distinguishing between similar images. The knuckle biometrics portion of the study concludes that the best extraction approach is a combination of probabilistic hue transform, or PHT, and speeded up robust features, or SURF. As we critiqued the study, we found the following strengths. The researchers clearly identified possible complicating factors for contactless biometrics as an identification tool, particularly differences in user skin tone, as well as use conditions such as palm and knuckle rotation and mispositioning. Their research approach sought to handle and minimize the effect of these factors. They also proposed a method that combined two contactless biometric sources for identification, presenting an option for system confirmation of user identity while still preserving the possibility of a purely contactless approach. And they employed overlapping techniques for feature identification and user images, reinforcing both image clarity and enabling the testing and reinforcement of individual feature mapping techniques. We identified the following weaknesses. The researchers did not present any information on how their approach might be integrated with other security methods for a particular system. For example, a banking site that uses contactless biometrics for mobile and the corresponding methods for desktops where video capture may not be available. Also, while the researchers argue that the use of palms and knuckles is reliable because they are not affected by emotion or fatigue, they did not discuss the potential impact of other complicating factors, such as injury or aging, on the reliability of this biometric approach. In conclusion, the study showed that both palm print and knuckle features may be considered as very promising biometric modalities which can be used in contactless human identification systems. The researchers have proposed an efficient algorithm that can be run on mobile devices that are widely available today. Thank you.